Okay. So here is about regression analysis. Okay. So regression analysis, what's going to do? Regression analysis is a statistical technique used to model the relationship between target variable and one or more input features. Okay, so you're looking for relationship or the mapping function that explain the relationship between target. Target means target variable means y. And one or more input feature mean x1, x2, the input features, and so on. Okay? Ni, ke, i, pu, ke, i. Right? Is it correct? No. Trying to do revision. It involves the process of learning a function, mapping function that associate input denoted as x with target denoted as y. Here y is the continuous and scalar. Yeah, so keep in mind if you are working on regression, the target should be continuous. Okay? Scalar value, meaning y, you have only single y. Can you have two y's? So if we have only one y, okay, how about if you have two y's? Is it possible to have y1, y2? Yes. Can have also y3. But this type of regression, we call it univariate. Univariate regression. This is, we call it multivariate regression. Okay, so it's possible to find mapping function that explain between two target variables, let's say, and input features. Okay, so in this case, I'm talking about regression again. This is for regression. How about classification? Yes, it's also possible. We're gonna find out what they call them. They don't call them univariate. They call them different name. Okay. So regression learns a function that maps the input, same, we are repeating the same thing. So here they're showing you examples where you have probably linear or nonlinear relationship. The relationship between variables can be linear, can be nonlinear. So what we mean by linear? Linear, simply the model you find is just representing by straight line. Straight line. So if this is the case like these two, then we call it linear relationship. What does it mean in lame language? Meaning the amount of changes, the proportion of the amount of changes on x, okay, versus y is same. The slope, in other words, the slope is same. Slope is fixed. Doesn't change. All right, the slope is fixed. If you look to nonlinear relationship, you have curve. So the slope here, the value as a value is different than the slope at this point, different than the slope at this point, and so on. The slope is changing over time. So here, what does it mean in real life? This is exponential, meaning as the value of x increases, the value of y increases exponentially. Okay? It's not just like amount of changes. If you have changes here or here, let's say five steps, maybe on y here changes 2 steps. Every time you have 5 steps changes on y 2 steps. This is fixed, so it's linear. While here it's not fixed. Maybe here, firstly, 1 or 2 step changes versus one step. Later it becomes maybe 2 versus 3, 2 versus 4. So the amount is changing over time. Okay, over time or over, yeah, going through x. Okay, as value of x increases, value of y, but all of them increases. So always there's a relationship. So in all of them, there's a relationship. Here there's a relationship, here there's a relationship, here there's a relationship. But whether it's just linear or nonlinear. Okay, so here is an example. Let's say you have input matrix, like the size and age of the house, and then you are looking for the price of the house. Okay, so here, as we said, these are the samples. Here are the dimensions. The number of dimension can determine the complexity of your problem. Okay, the complexity of the problem can be determined by the number of dimensions. If you have just one dimension, is simpler comparing if you have 100 dimensions or 1 million dimensions. Okay. Okay, so regression eventually, as we said, again, we are repeating same stories, right? So we have the mapping function. So again, this is univariate, remember, univariate regression. Why? Because you have one input feature, sorry, one target variable, one target variable, okay? You have only y, one y. So this is, we call it univariate. So here is showing you an example. If we have horizontal line, let's say we are trying to model this data. So this line is going to have theta 0 equal, theta 0 is going to equal 0, right? And theta 1 is going to be 0, because any value you substitute here, the output should be 0 all the time. Okay? Is this a good model? Definitely no. There's no model here. How the model should look like, probably, for this data, probably like this should be. You should find a line look like this, where maybe theta 1 is theta 0, some value, theta 1 is some value, okay? Which should explain or describe this line. How about if you find, so eventually what you are doing during modeling and evaluation, you're trying to find solutions. So maybe first time your solution looked like this. First time. Okay? And then you try again to find, maybe extract features or use other algorithms or whatever. So probably this is your second time, maybe you got like this. Still not so good. If you calculate MSE still high. MSE here still high. Error still high. The optimal one, probably this one, where MSE, can we say MSE equals 0 in this example? Cannot. Why? Anyone can tell me? Okay, good. We have one answer. How about the rest? Anybody can say this is, we should get for this example or any example in your mind, MSE here should be 0. Any example, huh? Maybe you say no, it's maybe a little bit like this. I don't care. But is it possible based on this data? No, no matter what you do, you will never get MSE. You know how MSE will be 0 in what situation? Can you redraw this data point to show where MSE would be 0? Anyone can tell? Let's say I just redraw again, and my data scatter points look like this. Okay? All the data points should be like this. So now, if I draw the line perfectly fit all the data points. If this is the case, where your data point located exactly on the line, that means there's no error at all. Then in this case, the MSE is going to be 0. Is it possible in real life? Impossible. Right? Because think about it. Let's say here you're looking to map the price of your mobile phone. Mobile phone price. Okay, and X here, let's say what's going to be? Brand of the phone. And assume each phone has only even single brand. How about this? Is it possible? Definitely no. Because you will see even the same brand, same model, each outlet may sell different price. So you will never get the exact same line, right? Never. So always you will have some error due to the noise. This is noise, huh? This is due to noise inside the data. There is pattern, but it's noisy because each outlet sells in different price. And they don't have clear picture why they are doing so. They may tell you due to our expenses, but can vary. Maybe I may expect, even if my expenses is 1,000, let's say, and his expenses is 1,000, I may sell eventually 1,200. He may sell 1,100, right? So there is no clear or definite value for the output. Okay? But we try to reduce the noise. So instead of considering 1,200, 1,100, what we could do, maybe take the average. This can reduce the gap between the noise. Or we can take median, like what we have done in the district house price. We took the median to reduce the noise because there are many variation, even if we have similar house, similar feature, but the price can differ. All right. Now, under regression algorithms, there are quite many. Those are some of the one that we're gonna cover in this course. So that you should be happy. You see, you have many algorithms and some more. Okay, so we have linear models. We're gonna talk about linear regression. Logistic regression, actually the name is confusing. They call it regression, but it's not applied for regression, for classification. That's why I put here, this is for classification, not for regression. Logistic regression is not used for regression in the sense that you're trying to predict continuous output. No, this is to predict categories. Logistic regression. Support vector machine, neural network, decision tree, random forest, KNN. By the way, all of these can be used for classification, can be used for regression. All of them, except the first one. So those are versatile. They call them versatile. Meaning can be used for regression, can be used for classification. Okay?